Hello! In this video, I'd like to go over a proof that I find really interesting, not because it does anything particularly tricky, but actually because it doesn't do anything tricky. At every stage of the proof, if you know what you're doing, it's clear what to do next. And so I want to walk you through this proof to hopefully give you a sense of how proofs work. This is a proof that came up in an Intro to Proofs linear algebra course that I TA'd under Dr. Narode. It was a really interesting course. There was a lot of row reduction in that course. Row reduction, as it turns out, is a really powerful tool, and I'll make a video on that at some point. But anyway, the proof that I'd like to show you is the proof that matrix multiplication is distributive. Now, there are some clever ways of proving this, but let's prove it in the most straightforward computational way possible. We have an equality of matrices. Let's restrict our attention to n by n matrices. Of course, this is true in general, but let's kind of simplify our work, and it'll be clear how to generalize this once you see the proof. But let's assume that A, B, and C are n by n matrices, and we need to prove that this equality holds for A, B, and C. Well, how do we show that two matrices are equal to each other? What's the definition of matrix equality? So we need to show that these two matrices are equal to each other. How do we do that? What does that mean? Well, that just means that all of the elements of the matrices are equal to each other. That's the definition of matrix equality. So in order to show that two matrices are equal to each other, we just need to show that for every appropriate pair of indices, ij, I and j going from 1 to n in this case, that the ijth element of this matrix is equal to the ijth element of this matrix here. Now we need to be a little bit careful because we're working backwards from our goal. Our goal is to get here, to prove this equality. And in order to do that, we need to prove this equality for all I and j. So we need to remember that even though we've written this down, this is not something that we have proved, this is something that we need to prove. This is kind of like one step away from our goal. We're working backwards through a maze. So it might actually help to separate these two so that it's clear that we haven't proved that they're equal yet, and our goal is to prove that they're equal. It's also important to note that we're trying to show that this holds for all I and j. That means that we can't make any sorts of assumptions about I and j. A common mistake that I saw with these sorts of proof problems was maybe picking specific I and j's as like an example, and then working through those examples and showing that it works. We need to show that this works for any I and j. And actually, more of what I saw was picking specific matrices, A, B, and C, and showing that this worked for those matrices. Again, we want to show that this works for any matrices, not just specific matrices, not just the specific examples that you can come up with, but for any matrices. And the way that we do that is we assign variables to the matrices, and we try to prove that our equality holds without making any sort of assumptions on our initial variables, on what sorts of matrices they are, other than, well, in this case, we're restricting them to be n by n matrices. But anyway, our goal is to prove that these two things are equal to each other, and all we have to do, just like we did with this equality, we just need to unpack definitions. In my career as a math student, a surprising number of problems that I encountered became so much easier if I just looked up the definitions of everything and tried to like unpack what it was that I was trying to prove. So let's use the definition of matrix multiplication to unpack this expression here. And it's just going to be this summation here, right? Because we're just using the definition of matrix multiplication. And I've been a little bit lazy here. Instead of writing, I really should write the sum from k equals 1 to n, and you should write that. But at some point with summations, you just want to write the sum over the variable And because we know that K is an index of these matrices here, and the indices go from 1 to n, so we know that K should go from 1 to n unless we've specified some other range for it to go through. So if you ever see a summation with just a variable below it, there's some sort of assumed range for that summation, and it's a sum over that range. But while you're practicing, while you're getting used to working with matrices and such, it helps to write the sum from k equals 1 to n. Similarly, I'm going to want to unpack this term here using the definition of matrix addition. Right? The ijth element of the sum of two matrices is just the ijth element of the first matrix plus the ijth element of the second matrix. Right? That's the definition of adding two matrices together. We just add corresponding elements of the matrices together. And we keep going, trying to rewrite this side and trying to rewrite this side in hopes that we get the same thing at the end. Here I'm interested in the kjth element of b plus c. And that's just going to be, it's the same thing, the kjth element of b plus the kjth element of c. And these two products we can expand out using the matrix multiplication formula. Sometimes when you have two different sums, these are completely independent sums. From each other. Sometimes when you have independent sums, you'll want to use the same variable. In this case, we want to use the same variable. Sometimes you'll want to use different variables. Maybe a sum over k and a sum over, I don't know, L or M or something. So we've gotten to the point where using the definition of matrix equality, matrix multiplication, and matrix addition, we've turned this problem into a problem not involving matrices at all, just involving the properties of summations and some basic algebra. Right? And that's what I mean by unpacking a problem by using definitions. We've turned this into a problem that doesn't involve matrices at all. We've taken things that we were less familiar with and turned the problem into something about things that we're hopefully more familiar with. Certainly the algebra we're more familiar with. Summations, it's okay if you're not quite familiar with them, but they have some really basic properties that just involve the fact that they're just adding a whole bunch of things together. All of these elements here, all of these things here, these are just elements of matrices. So all of these expressions are just expressions involving real numbers. So this is just a question about sums of some algebra involving real numbers. So we've done all of kind of the straightforward steps. We've done all of the unpacking. This is kind of, we're trying to show that these two things are equal to each other. So we're kind of trying to make our way from here to here by valid algebra steps. We're kind of trying to work our way from a start to a finish through some sort of maze. What we're doing over here is we're kind of working backwards from the goal. If you're trying to solve a maze, you want to kind of work forwards from the start of the maze, but also work backwards from the end of the maze, and hopefully you can kind of meet in the middle, and that'll give you your solution. And we've kind of taken the obvious steps from the start and the obvious steps from the end, and now we have to hopefully connect these two things somehow. So how can we do that? Well, let's start by using a property of summations. We know that if we're adding a bunch of stuff plus another bunch of stuff, that's the same as just having one big sum. This is a little bit easier to see in reverse, but essentially we're just adding a bunch of things in a slightly different order. Instead of adding all of these terms first and then adding all of these terms, we are instead adding all of the terms at the same time. So a little bit tricky, especially if you don't have a lot of practice working with summations, but hopefully this makes sense. It makes sense why this is true, and it's also kind of a pretty straightforward thing to do, to turn two sums into a single big sum, the sum of a bunch of terms. And now, hopefully you see that this side is equal to this side just by distributivity. We haven't, these are real numbers, remember. So we know that with real numbers, I mean, we're trying to prove this for matrices, but we know that real numbers distribute. And so because these are all real numbers, this side is equal to this side, right? We're distributing the aik over, and we get aik bkj plus aik ckj, which is exactly what we have over here. So this is kind of neat. At the core of the fact that matrices are distributive is the fact that real numbers are distributive. Or, I don't know, if your matrices had complex numbers as elements, you could use the fact that complex numbers are distributive. The proof would look exactly the same. This is actually kind of one of the nice things about having proofs. One of the reasons why it's really nice to have proofs is that it makes it clear how we can generalize things, right? I was assuming from the start that A, B, and C were matrices with real numbers in them, but at no point did I actually use that assumption that these were real numbers. The only assumptions that I used were that, addition and multiplication work the way that we hope that they do. And so if these elements are complex numbers, that's perfectly fine. This proof works exactly the same. Now, before you go submitting this sort of proof for your homework, we should clean it up a little bit, right? Our goal was to show that we can get from the start to the finish via valid algebraic steps, but it would be nice to present this as the path from the start to the finish. And instead of saying, oh, follow this path here, present it as a linear path. So we're going to want our chain of equalities to look like this in our final proof. And of course, we're going to want to label why each equality holds so that it's clear what we did at each step. So a proof that matrix multiplication is distributive should look like something like this if you write it up. Now, this actually wasn't the proof that really struck me as very straightforward. Again, there's this step here that really, it is pretty straightforward, but it's not like immediately obvious. It's not like, oh, we have a product of matrices and we need an element. Let's use the formula for an element of the product of matrices. It's not immediately straightforward unpacking definitions. The proof that struck me was actually the proof that matrix addition was commutative. And the proof is actually so straightforward that I'd like to let you do it, hopefully getting something in the end that looks a lot like my example solution for matrix multiplication is distributive. I'll link to a full write-up of that proof in the video description below if you want to check your answers, and hopefully you'll come to appreciate that just like how in algebra, sometimes it's like immediately obvious what to do next. Like, oh, it's clear that we should do distributivity here because it's a setup for distributivity, and our goal is to expand everything out. Similarly, when you're doing proofs, sometimes it's immediately obvious what to do next. Not always, certainly not always. But sometimes it's pretty straightforward, and once you get the intuition for it, hopefully working with proofs will be as straightforward as just doing basic algebra. So, thanks for watching. Please leave any questions or comments down below, and be kind to each other.